right, let's wrap up this section with limits at infinity and horizontal asymptotes with one more example and the precise definition of these limits at infinity. So let's just do this example. This will kind of combine a few different things, not just from this section, but also from our previous sections when we talked about infinite limits. So not just limits at infinity, but infinite limits. So this particular example, let's determine all the asymptotes of this function. So we've got a function, a root 1 plus 4x squared over 4 plus x. And we want to find not just the horizontal asymptotes, but let's find all of the asymptotes. So here's the little piece of review, right? When we talk about asymptotes, we've got our vertical asymptotes. That's where we have infinite behavior of the function. So vertical, let's look at our vertical asymptotes. And that's where the limit of the function approaches positive or negative, has infinite behavior, and technically this could be just one-sided as well. So we're looking at limits of the function growing or decreasing without bound. And then let's also consider our horizontal asymptotes. So our horizontal asymptotes are going to be looking at the end points of the graph. So let's consider what happens as we approach both positive and negative infinity of the function. Okay, so we'll have to look at both sides there. And so let's see what happens there. See if we have a horizontal asymptote, if the function is approaching a single value as we head out to the far ends, both the left side of the graph and the right side of the graph, as x increases without bound and decreases without bound. So let's start with the vertical asymptotes. Those go back a couple of sections, but starting with the vertical asymptotes, when I look at this function, I notice first of all that we have an issue when we have division by 0. So let's consider what happens when the denominator is actually equal to 0. And so that would be when 4 plus x equals 0 or at x equals negative 4. Right? Maybe not instead of or at, just that's what that implies when x equals negative 4. So what happens there? Well, let's look at it. What happens to the limit of this function f of x, the square root of 1 plus 4x squared over 4 plus x, as we approach negative 4 from the left? And let's also take a look at it as we approach negative 4 from the right. So 1 plus 4x squared over 4 plus x. Zoom in a little bit. So as we're doing that, we're considering what happens both on the left side of negative 4 and on the right side of negative 4. And so just kind of thinking about what this means, right? On the left side, right, that's my little thought bubble. My thought bubble would say we're plug in a value, you know, it's just so that you can actually have a number that you're thinking about. You're the left side of negative 4, so a little to the left of negative 4, you're plugging in something like negative 4.001, right? So that can kind of be going on in your head as you're working this, and you can say, well, the numerator itself, notice in the numerator we have 1 plus 4x squared. So this quantity in the numerator is always positive. And so we have no issues with that. We don't have to worry about the domain on that guy with that square root, because you do have to guarantee with an even root that your argument is always positive. But in this case, it is, because the x squared is always positive, multiply it by 4 and add 1, just even more positive. So this is always positive. And so the numerator, we can just use direct substitution. And let's see, that's going to become 1 plus 4 times negative 4 squared. So in the numerator, I just get a positive, what would that be, 65. So square root of 65, a little bit more than 8, because square root of 64 is 8. And then in the bottom, as I'm plugging in these numbers, little to the left of 4, and then taking 4 minus something like that, right? Because we are, you know, it'll be plus a negative. We're going to get something that gets really tiny from the left, right? It's something zero, it's approaching zero from the left. It's really tiny, but it's negative, a very small negative number. So taking a positive square root of 65 and dividing by something that approaches zero in a negative way is going to give me that negative infinity. So I have a negative. So that's definitely right away. I already know now that this is a vertical asymptote because I have infinite behavior on one side of the graph. But to complete this out, since we're finding the vertical asymptotes, we know this is a vertical asymptote, but it's good practice just to show what happens on both sides. So does it decrease without bound on both sides, or does it have growth without bound on one side and decrease without bound on the other? So let's just consider what happens on the other side. So in this case, we're going to be plugging in values like x equals negative 3.99. As we're coming from the right of negative 4. So we're thinking of something like negative 3.999, very, very tiny numbers. If that helps you to think about an actual number, then you can do that. Again, the numerator, though, is going to be exactly the same. We can just use direct substitution in the numerator. And so the numerator is just going to be the square root of 65. Now in the bottom, as I plug in something just a little bit to the right of negative 4, so something like negative 3.999, and then take 4 plus that negative 3.999, or something just a little to the right of negative 4. This is going to get really tiny, but coming from the right side of negative 4, this is actually going to approach 0 from the right. This quantity in the bottom is going to approach 0 from the right. So as we get very small but positive and take a positive quantity and divide by a very tiny positive quantity, this is going to approach infinity. So we do know that we have a vertical asymptote here, but we know that from the left, it's going to be approaching negative infinity or decreasing without bound, and from the right, it's going to increase without bound. Capture that by saying it's approaching or going to infinity. All right, but all of that says that we definitely have, so our vertical asymptote, our one place where we have a vertical asymptote, or a VA if you want to abbreviate, a vertical asymptote, the one vertical asymptote for this function is at, and we always want to write these as equations. We don't just say negative 4 because is that vertical or horizontal? You have to define it as an actual line. So x equals negative 4. So our vertical asymptote is occurring at x equals negative 4. And we have just one. And we have shown all the behavior around negative 4 above this as well. So it's a very complete showing of our vertical asymptote. So we know we have a vertical asymptote at negative 4. Now let's consider what happens at the ends of the graph. So we've got this function. We know we've got a vertical asymptote at negative 4. What about our horizontal asymptotes? So our horizontal asymptotes, we have to consider both sides of this limit. So we're going to have to consider the limit as x is approaching infinity, going to the right side of the graph, of the square root of 1 plus 4x squared over 4 plus x. And we will also have to consider the limit as we decrease without bound and go to the far left of the graph. Okay, so once again, we have worked with infinite limits on several examples now, and one of our techniques is to look at what is happening in the denominator and think about which of the terms in the denominator essentially dominates the denominator. Is the highest, if it's a polynomial, you can think of it as the highest degreed or the highest powered, or if it's just a function other than a polynomial, you can look at it and determine from the types of terms that are in that denominator which one is going to dominate. This is clearly a polynomial. It's just simple linear. So the highest powered term here would be x. So what I'm thinking here is I'm going to go ahead and I'm going to divide everything by x. I'm going to divide all of the terms in this entire expression, including this entire root in the numerator, by x. Now, another way to say that, of course, is that we could have just multiplied top and bottom by 1 over x and then distributed. I just did those two things all at once. I'm going to zoom in so I have a little more space here. So this is going to, now we're going to continue this out. This is just a way in which, you know what I didn't do is I didn't talk about how if we at the very beginning had just plugged in infinity, I would have actually gotten something like infinity over infinity. So if I had just tried to plug in essentially, let x grow without bound, what I would have found is that both the numerator and the denominator approach infinity, which it's just not enough, right? This just simply means do more work. I normally write that out for you guys, and so I'll do it again. It means just you got to do some more work. You got to do something else. I jumped right into my technique. I sort of glossed over that part, but we've done so many of them. So heading on, right, jumping back into where I was at with my technique, I'm going to end up with the square root on the top of 1 plus 4x squared divided by x. And then on the bottom, I'm just going to have 4 over x plus 1. Now I need to continue to do some algebraic simplification in the top right here. And I want to bring that x inside the roots because I want to be able to divide. I want to take 1 and 4x squared and I want to divide by this expression that I'm dividing, but I can't do that until x is under a square root because you can't, right? If you have the square root, side note, if you have the square root of something and then something out here outside the square root, you can't bring that into the square root until they are both under a square root. Okay, so that's what we got to do. So we worked with this on another example, and I'll make a little star right here. And we'll come over here and say, note that we are approaching infinity. X is approaching infinity, which means that x is positive. And so x is greater than or equal to 0 for this particular limit. Going the other direction, we'll have to consider when x is negative. But we're definitely approaching infinity, and we know by definition that x is actually equal to, actually let's write it this way, the square root of x squared is equal to x. Okay? Since x is positive. Remember, when you take the square root of x squared, you get back a positive number. So if x is positive, it will be equal to exactly x. Okay, so this is our little note. We got to remember when we make these changes, when we rewrite a variable in a different form, we have to consider the fact that we don't know the sign of it. Or if we know the sign of it, we have to make sure that we utilize that when we're rewriting this. And we do. We know the sign of x is positive here because we're approaching infinity. So I am going to make that substitution. So I'm going to come in here and I'm going to write it just, we could erase, but let's go ahead and just rewrite it. So I'm going to take 1 plus 4x squared and I'm going to rewrite x as the square root of x squared. That's going to allow me to do the algebra I want to do and finish this limit. So this limit now, as we're letting x grow without bound, becomes the square root. I can now bring that underneath 1 plus 4x squared divided by x squared. And here I am going to, rather than rewrite, I am going to just continue to simplify. Here I can actually divide each of those terms by x squared. And so what I will end up with is 1 over x squared plus 4. And in the bottom, I have 4 over x plus 1. And now I can actually take this limit, whereas in the beginning I had that infinity over infinity. That is not going to be the case here because we have constants divided by quantities that are growing without bound in a couple locations here. And we know that those will decrease to 0. Those will become 0. They will approach 0. They will get tiny. Right? And so then this is going to be equal to the square root of 4 over 1 or positive 2. And so that's my limit, which tells me, again, remember, we're looking at what's happening. We're saying the function, the function is approaching, somehow, is approaching as we go out towards infinity. Here's our x-axis. Here's the function. We're saying that this function is approaching this value 2. Okay, just to have a visual. This function is approaching this value 2, which means that that is a by definition, that is a horizontal asymptote to this graph. So our first horizontal asymptote, I'm going to just write HA right here. So we've got a horizontal asymptote at y equals 2. We'll summarize it at the end because I think we're going to have another one as well because we have to consider what happens on the other side of the graph. This was the right side of the graph. What then is happening on the left side of the graph? So let's take this same limit. Maybe try to keep this on the screen if we can, make it just a little bigger. We're going to take almost exactly the same limit, but we're going to let x decrease without bound this time. But the process is going to be very similar. We just have to remember we're on the left side of the graph and x is negative because we're decreasing without bound. So we're going to do the same thing. We're going to divide everything, multiply everything by 1 over x, highest power in the denominator, distribute. I'm going to do all of that at once just to make the work a little more simplified here. A couple less steps. And I'm going to bring that in, limit as we are approaching the limit of the function is we're approaching negative infinity or decreasing without bound, and that is going to become, I want to try to keep this up on the same screen so that we can see all this and how similar it looks, and also point out where it's a little different. So notice here, I want to do the same thing that I did up above. I want to do the same thing. I want to be able to bring that x underneath the square root, but I can't do that. I can't put x under a square root without considering its sign. So little star right there, and I'm going to make a similar note to what we have right there on the top of the screen. I'm going to say note that x is this time decreasing without bound. It's going to negative infinity, which means that x is less than or equal to 0. X is negative in this case. And therefore, when we take the square root of x squared, to make sure that we get back a negative value, I have to put negative. Okay? So x is actually going to be equal to the negative square root of x squared. And so when we come here and we make this substitution, I have to make the substitution, I have to include the sign because I know my x's are negative. So the limit of this function as x decreases without bound is actually going to be the square root of 1 plus 4x squared. I'll do this in red just to make it really clear. We can replace that x with the square root of x squared, but because x is negative, we have to include the sign. Because taking the square root of x squared, by definition, comes back out as positive, and so we have to guarantee we have that sign. Then we have our 4 over x and our 1, and we can continue this through, but we have this one slight little difference where we've got that negative sign, and so this entire square root here becomes the square root, it's going to have a negative sign. I'm just going to pull the negative to the front, divide 1 over x squared plus 4, and then we have our 4 over x plus 1. And when I take this limit, I end up finding that this becomes negative square root of 4, because each of these, again, is going to approach 0 as we let x decrease without bound. As x approaches negative infinity, goes to the far left of the graph. Each of those little terms, a constant over x raised to any power, is going to go to 0. So this is going to be the square root of 4 over 1, which is negative 2. And there is our second horizontal asymptote. So we have two horizontal asymptotes by checking both sides. So our horizontal asymptotes here, we have to check both sides. And since we checked both sides, and again, I'll circle that note that we used. Since we checked both sides and found that we actually, sometimes you have the same horizontal asymptote, or you don't have one on one side, or you don't have one on, you don't have to have a horizontal asymptote at all. But in this case, we ended up with, for our horizontal asymptotes, we ended up with, and again, we have to define these as lines, right? We don't just say negative 2 and 2. We have to say y equals negative 2 and y equals 2. We have to define them as horizontal lines. And so those are my horizontal asymptotes, checking the two endpoints of the graphs. So to find the horizontal asymptotes, we have to go to both the far right and the far left by looking at limits at infinity. And to find the vertical asymptotes, we have to figure out where there's infinite behavior. And in this case, since it was a rational function, we had to check where we were having that division by 0. So let's see if I can get this all on the same page. It's going to be pretty small because my work got kind of long there, but we can get that example on one page right there. And we can see that we have our two horizontal asymptotes and our one vertical asymptote. And that is the process for finding all those asymptotes. Good review of all of our limits here that deal with infinity, both limits at infinity, but also infinite limits. And just grabbed a graph of this real quick to throw up here on the screen too. Here is the graph of that function that we just algebraically and with some calculus principles using limits showed where the vertical, we showed a vertical asymptote at -4, and we showed the two horizontal asymptotes at 2 and -2. And you can see those, I just used a graphing program here to grab this little graph, but we could draw in, there's y equals 2, y equals line's not exactly straight. Y equals -2, and here is our vertical asymptote right down here. And in a couple of sections, we're going to get heavily into using calculus to graph, and we'll come back and we'll talk about how we start here by finding those vertical and horizontal asymptotes, and they give us sort of a skeleton to the graph, and then we're going to use some other calculus tools and techniques to fill in the rest of the graph. So, but this finding those asymptotes gives us sort of the skeleton to work within as we're graphing. All right, I'm going to end this video with the two precise definitions for a limit at positive infinity and a limit at negative infinity. We are just finishing out coming off of a section where we talked and spent some time actually proving the limit at a point using the precise definition with the epsilon and deltas. So hopefully this will kind of fit into that in your mind, fit into that same category of precise definitions, where we're going to use this generic epsilon and we're going to force a function to be within an epsilon neighborhood. But this time we're not looking at it at a specific point, we're looking at it at infinity, and the other definition will be at negative infinity. And so here basically what we're saying is, just given an epsilon, if we have a limit, so if we say that the limit of a function as we approach infinity is L, what that means for us is that given any epsilon, there is a number, this time we're going to call it n, there is a number such that as long as x is greater than n, f of x minus L will be less than epsilon. So what that is saying is that here's our n if we've got a graph, and if we have a limit, meaning we have a horizontal asymptote as x approaches infinity, the function gets infinitely close to this value L as x approaches infinity, as x grows without bound. What that means is, given any epsilon, you can find a value n so that as long as your x's are to the right, bigger than n, then your f of x's will be in the appropriate neighborhood. So rather than finding a little neighborhood around a point, like in our previous precise definition at a point, what we're saying here is, as long as you can find a value n and you can push your x's further out, that puts you in the correct neighborhood on the y-axis, then that means you have a limit. That is the precise definition. And if you shrink epsilon down, it just means you're probably going to have to move n further out. Okay, so as epsilon gets smaller, you're just going to have to make your n bigger, and so that your x's are even further out along the x-axis. And in a very similar way, we have this precise definition as well. Going the other direction, it just simply says that if we have a limit, if the limit of a function as x decreases without bound goes to negative infinity, if we have a limit that's equal to L, that means that there exists, for every epsilon greater than 0, there exists a value n such that if x is less than n, in this case, we're going this direction. So as long as x is over here to the left of n, then our f of x values will be in the appropriate neighborhood on the y-axis, in our epsilon neighborhood on the y-axis. If you shrink epsilon down, that simply means you're going to probably push n further out here so that this neighborhood gets even more restrictive. Okay? And that is the way we precisely define limits at infinity and negative infinity.